Okay, this is 15.2 Part B. This is line integrals of vector fields. So I'm going to approach this the same way we did 15.2a, which is to talk about a situation in which we might want to measure something, give the notation for the integral and the name of the integral that represents it, and then talk about a method of evaluation. So here's the situation. And so I'm going to do a two-dimensional picture for this just because it makes it easier, but absolutely this will work in 3 dimensions too. So suppose, sorry about that right there, suppose that capital F represents the flow of a fluid. And suppose that a curve C, this will represent, let's say, the route that an object takes through that fluid. Let's say the path of an object, this has a direction through the fluid. So here's like an example. And so I'm going to do this without an axis, just because the axis is sort of cluttering. So imagine that you have your vector field like this. Maybe it curves around. Maybe over here it keeps going to the right. And let's suppose then there's an object now that's traveling through that fluid. So maybe something like this. Maybe it begins here, and it travels, maybe it gets swept up by the fluid, and then maybe it fights against it for a while, and then it goes with it, and then maybe it turns around and goes back like this. Maybe it stops right here. So the path that it takes will be something like this route. So there's a direction in mind, a beginning and an end that are definite. And so if you imagine this, so you could, for example, picture the blue as like the flow of a river or something like that when you're looking from above, and maybe red is the route that like a small boat takes through the fluid. So what we see is at each point some work may be being done by the fluid on the object, and in some places the work is negative, in some places there's no work, and in some places the work is positive. So let's say the fluid does work on the object as the object moves. So just to point out a couple of specific examples. So just so we know, the work could be positive, could be negative, could be 0. So in general, work is force times distance. In this particular case, of course, it varies. So just to point out some specific locations. So at this point right here, the object is moving in the same direction as the fluid. So that's going to be a positive work. Right here, it's perpendicular. The fluid is not doing any work on the object because it's acting perpendicular. So the work right there is 0 instantaneously. And then sort of like right here, the object is going against the flow of the fluid. So the fluid is doing negative work here. And so what we might ask is, over the entire route, how much work is done? So here's the question. As over the entire, let's say, journey of the object, what is the total work done? By F. So the notation for this So this is sort of a weird one, and there are two different notations that are commonly used. So suppose f, so I'm going to give f, like we did before, an m, an n, and a p. Suppose that's our f, and suppose c is a curve with direction. So then the work done by f on c, I'll say on c, but we sort of mean by by f on the object that's following c, but we can say by f on c. This is denoted so there are two different notations. So sort of the maybe standard notation is just the integral over c of f dot dr. This is very weird that we have a dot product in this. The reason for this, as we'll see, is that the notation is giving us a set of instructions. So the reason for having this, it's not as weird as it looks, right? Or this is sort of a bit weirder, is the integral over c of m dx plus n dy plus p dz. Now this is just notation. This is strange notation, this second one. It does not mean that you integrate them each with respect to their particular d's. So you're not integrating m with respect to x, you're not integrating n with respect to y, and so on. It's just the notation. So just to give you an example of how this notation arises, so without doing any questions, I just want to give you two things that mean the same. So the following mean exactly the same. Oh, just to be clear, because I didn't give you the right phrasing here, both of these are the line integral of f over or on c. That's the term. So the following mean exactly the same. So so you see the notation. So if you were to see this, the integral over c of xi plus xyzj plus say z squared k dot dr, this means the same as if you were to see the integral over c of x dx plus xyz dy plus z squared dz. This isn't saying anything about how to evaluate them, how to evaluate either of them. It's just saying these two integrals, these two notations, if you like, mean precisely the same thing. They're both measuring the work done by the vector field on the object. And one thing to point out here, in the second one, it's not as obvious that there's a vector field hidden in here because the ijk's have vanished, but there's a vector field here. Right, it's the same vector field as above, right, this one. So please keep that in mind. Now, next thing then, of course, is how do we evaluate this? So 3, method of evaluation. So it turns out of all the integrals in this chapter, this is the one that has the most options. So this is going to sound overly threatening when I say it, but don't panic. It turns out there are 4 different ways to do these depending on the circumstances. And so those circumstances will become really, really clear as we go through them one by one. This is why you shouldn't panic. But there will be multiple ways, right? There will be 4 ways to do these, depending on the situation. So really, the situation is not that you could do it any of them, but in certain situations, specific ways will be the best ways. So there'll be 4 ways depending on the circumstances. So in this section, this is sort of the most basic way. You could kind of think of it as maybe the long way, but it will always work. Sorry, that's a terrible thing to say because it's liable to make you think you can always do it this way, and you almost certainly don't want to. This is the most basic way, but it's really the way of last resorts. The other ways will all be shortcuts. if you like, is maybe a good way of thinking about it. So just like in 15.2a, what we do is we parameterize C. So this will have an R of t. This will have, just like before, in 15.2a, x of ti, y of tj, z of tk. This is with t between a and b. So then what happens is this. So we've got this integral. So I'm using the first notation here. Got this new notation. So what happens is the following. The notation will tell us what to do. So this will turn into an integral from a to b. Now, the vector field f has x's and y's and z's in it. Those will get replaced by x of t, y of t, z of t. Then we have a dot product, because the notation says dot product. Then it says dr, and so what happens is we actually put in the derivative of r. We dot those two, and then it's with respect to dt. So the thing to see here, really important thing, is that this result right here, this is the scalar function of just t. The vector has gone once you dot. So let me look at an example, and then I want to do the same example with this other notation, because it may look like things are different depending upon the notation, but they're not, right? So here's an example. So I'm going to make this first example really, really simple. I'm going to give you the parameterization, just because really what I want us to see is how we get the final integral. So let's say find the work done by the field f of xyz equals xyi plus xj plus, say, yz squared k on the particle following the parameterization. R of t equals, say, t squared I plus square root of tj plus 2tk for t between 0 and 4. So all I'll do is get to an integral. I make no guarantees this integral will be pretty. The point is just to get to it, right? So we have the parameterization. All we need is the derivative first. Well, first we need the derivative. We do not need the magnitude like in 15.2a. Here we just need the derivative. So this is 1/2 t to the minus 1/2 here for the j and 2k. So then what happens is the integral over c. So the mass, let's be clear, oh sorry, the work is the integral over c of the vector field so yz squared right there dot dr. This is just the notation, right? So this right here is this notation right here. And what this is equal to, according to the change, is this becomes an integral from 0 to 4. That's a to b. So this is the really icky part. Is this vector field, all the x's and y's and z's get replaced by, let me color the heck out of this thing, right? So the x's get replaced by this x of t up here. The y's, which are right here and right here, get replaced by the y of t up there. And the z right here gets replaced by the z up here, back in the parameterization. So what this whole thing turns into, and this is still a vector right now, so x is t squared, y is square root of t, that's I, x is t squared, that's j, y is square root of t, z is 2t, that's squared, that's k. So this all gets dotted with this derivative we just took. And this is dt. So it's horrible, right? But just to clarify, let me get some other colors. This derivative, this guy goes here. Then when we dot these, which I'll do because it's messy, but it's okay. This is now the integral from 0 to 4. So then we get t squared times the square root of t times 2t plus t squared times 1/2 times t to the minus 1/2 plus square root of t times 2t squared times 2 dt. I mean, this isn't actually terrible, but it's terrible looking. But the thing to see here is that this is nothing more than like an integral, it's a regular calculus 1 integral. Just integrate as in calc 1. And that's it. That's the final answer. So what I want to do is I just want to show you this same problem with the other notation, just so you see that the other notation is also telling you what to do, just sort of differently. So here's the alternate notation. The only thing that would be different is the way that we wrote the integral would be different, right? So we'd write the integral So what I'm doing is I'm going to rewrite, let me circle it for now, because we're sort of done with it, so it doesn't matter if we trash it a bit, I'm going to rewrite this integral in the new notation, or the alternate notation. So in the alternate notation, this would be the integral over c of x, y, dx plus x, dy plus y, z squared, dz. Now, if we look at this notation, what this notation is also doing is it's telling us what to put where, right? So this notation is saying everywhere you see an x, put x of t. Everywhere you see a y, put y of t. Everywhere you see a z, put z of t. Everywhere you see a dx, put the derivative of x of t, and so on. So what we do is we replace x by x of t, y by y of t, z by z of t, dx by x prime of t, dy by y prime of t, dz by z prime of t, and those all come from, pick a different color, they all come from the parameterization. So when we do this, so see what happens, right? I still get the integral from 0 to 4 now, and then I see an x, so I put a t squared. And I'm reading through this guy up here. So I see an x, I put a t squared. I see a y, I put a square root of t. I see a dx, I put a 2t. I see a plus. I see an x, I put a t squared. I see a dy, put a 1/2 t to the minus 1/2. I see a plus. I see a y, which is a square root of t. I see a z squared, which is 2t squared. I see a dz, which is 2, and then I dt it. And if you see that, right, if you take a look, this is exactly the same result. This guy is exactly the same as this guy. Right, so the results are the same, right? The integrals are the same at the end. They're just this thing that you evaluate, right? So they're the same. So both notations are used. Both are ones you want to be familiar with. Both will come up in problems. They come in the book. They come up in old exams. They could potentially come up in your exam. Just be aware of them. And be aware that this is only one of 4 methods that we'll have for evaluating these. So let me just do one more, and then I want to make a couple of closing notes. So let me clear the screen completely before I do the next example. So next example. Let's find, let me think about this, something good. Let's find the work done by the vector field. Let's make this nice and two-dimensional. Makes things a little more sane for a good closing example. Say x plus y I plus y cubed j on the particle, let's say following the straight line from 1, 2 to 8, 7. So first I need to parameterize the line. So there are multiple ways to do this. The standard way is to use two linear functions. They'll both begin with the coefficient of the starting point. So I'm going to have a 1 and then the vector that gets me from the beginning to the end. So from 1 to 8, I need 7. So it's 1 plus 7t. And from 2 to 7, I need 5. So that's 2 plus 5t. That's j. And that's t between 0 and 1. So if it's a bit fuzzy, you may want to look back at some of the parameterizations of curves from earlier sections. But this is not a hard one to see. When you plug in 0, you get 1, 2. When you plug in 1, you get 8, 7. So it works out nicely. Right? So once we have this, we can use any notation we want. Let's use the dx, dy, dz notation. Right? So either notation. Let's do the second. Right, the work is the integral over c. So this becomes x plus y dx plus y cubed dy. And this is this vector field baked into this integral right here. Right there. Because remember, there's a vector field hidden in the integral. And so this is the nice notation in the sense that it just tells me what to do. Right? I get the integral from 0 to 1. And then I go, okay, I see an x. Let me put in 1 plus 7t. I see a y. Let me put in 2 plus 5t. I see a dx. Let me put in the derivative of x. This is 7. I see a y cubed. Let me put in, the y is 2 plus 5t. That's cubed. I see a dy. That's 5. This is now dt. Right? So just to clarify, if I lost you all a bit there, this is my, I'm thinking of this as my x. Thinking of this as my y. So here's the x. Here's the y. Here's the dx. Here's the y cubed. Here's the dy right there. And again, I'm not going to evaluate this to completion. This is just an integral involving t. And that's that example. So let me just close with a couple of closing notes. 3 in fact. So first, actually I'm going to break them into 2 instead of 3. It's a little bit better. So the first is that the parameterization of C, actually maybe 3, well, we'll see. The parameterization of C doesn't matter, but the direction does. So in other words, the direction is the only thing that matters. So let's put it this way. When parameterizing C, get the right direction. Right. If you have the right direction, the parameterization doesn't matter. Second thing, if you go the wrong direction, you will get the negative answer, which makes sense because if you think of what happens with work, if you reverse direction in the fluid, the work will always be opposite, right? So if the direction is reversed, the result is negative. Right? So sometimes this can be written as follows. We can write the integral over negative c of f dot dr is the negative integral over c of f dot dr. This is just a fancy way of writing this. All that this means is when we write this thing right here, negative c, this is c, but with opposite direction. So all this is saying is if you flip the direction of the curve, you negate the result. And then the last thing is actually related to 15.2a as well. It's to be careful about notation. So just to illustrate, let me show you three different integrals. So look at the difference between this, and this. These are all totally different, right? And they look surprisingly similar, right? So the first one of these, this is a regular Calc 1 integral. The second one, because of the d little s, this is the line integral of a function. This is 15.2a. This, because of sort of the weird combination, this is nothing more than the line integral of a vector field. This is really meaning this. Which is the same as meaning, or if you prefer, xi dot dr. So be aware of that these are different. And typically, like, I'm not going to try and mess with you and sort of confuse you and give you one instead of the other. But this is why notation is always so important, and why in calculus we're always saying, oh, don't forget your dx's, don't forget this, is because now all of a sudden we have these new integrals appearing. And if you confuse your notation, you will confuse yourself or other people as to what you mean with these things. So that's the end of that section. That's the end of line integrals of functions and vector fields.